Hello, in this video we are talking about net force analysis. Now that we know a little bit about all these different forces, how do we put it all together and do some math with it? Because that's what we're here for after all. This is physics. We're just dying to do some math. So we're going to look at what happens when a bunch of forces are acting on one object and how we analyze that with the beautiful free body diagram. All right, so a free body diagram is the main tool we use when there's forces acting on an object and we want to figure out what that does. We draw a free body diagram. What this is a simplified diagram that shows all the forces acting on one object. So we're going to draw the forces as vectors, which means we're going to be drawing some arrows. So the direction of the vector, the arrow that we draw, shows which way the force is pushing or pulling, and the length represents the magnitude of the force. So a longer vector, longer arrow means a larger force. You want to do your best to roughly draw these to scale. It doesn't need to be perfect. If one force is definitely bigger than the other, the arrow should be obviously longer, but you don't have to worry about, measuring them exactly and making this arrow 1.7 times the size of the other arrow or something like that. All right, typically, especially with the IB, force vectors are drawn from the point of contact. We'll look at what that looks like. Like if there's a force from the ground, you draw the arrow like starting from the ground, that kind of thing. You will sometimes see them, though, again, especially outside the IB, as like a point, treating the object as a point mass. You're going to just draw a point, and from the point, draw all the different forces in the directions that they're moving. That's another fair way to do it. Okay, so let's look at some. Here's a classic physics problem. There's a box and you're like pulling it across the ground, as you do. So we got our good old applied force here. So something is pulling this way. It could be whatever. Somebody's pushing it, somebody's pulling it. As it moves, it looks like there's a friction force. So notice that's drawn like along the ground because the friction will act between the ground and the box here, parallel to the plane of contact. We got a force due to gravity straight down, of course, because we're assuming we're on the surface of the Earth here, and the center of the Earth is that-a-way, down. And we have a normal force, which is, again, drawn from the bottom because the normal force acts from the ground and pushes up perpendicular to the surface. Force due to gravity always comes from the center of mass. All right, here's another one. How does R2-D2 fly? Like this. There's some kind of like thrust force and then a gravity straight down. There you go. So that's another one showing two forces. And here's a fun one where we have a person on a ladder and there's a whole bunch of forces acting. So you can see a lot. And this is, we can see the sort of problem diagram or just a diagram of what's going on, and a free body diagram, which is a simplified view that looks specifically at the forces on the ladder. All right, so FBD is only ever going to be the forces on one object. We don't care about the forces on this person. If we did, we would have to draw another free body diagram. So this is just the forces on the ladder. So let's see. We got the force due to gravity, the weight of the ladder itself. We got FM, which I'm thinking is force of man, who's standing on the ladder, and certainly there's a force down from that. Two normal forces. Look at that. There's a normal force from that wall pushing to the right, because remember, it's always perpendicular to the surface. And we got another normal force down here from the ground, and also friction. Friction will be holding, keeping this ladder from just like sliding and this man falling to his doom, right? All right, so a whole bunch of different vectors and different ways to draw them with the points of contact and so on there. Okay, so once you got your FBD, what do? Well, what we care about is the net force, the sum of all of the forces acting on the object. So net force, resultant force, both mean the same thing. And it's a math idea of taking all the forces acting on an object and, and adding them together. Okay, but we do add them in a specific way. It's vector math, which is a little different than straight up algebra or arithmetic. So we'll look at that. Essentially, we need to add in a straight line until we get a little fancier. So remember, Newton's second law talked about a net force and said, Newton's first law says if there is no net force, then nothing changes. The object keeps moving the way it's moving or not moving. But if there is a net force, then the net force causes an acceleration according to usually F equals ma. Remember, if mass is changing, we got to use the more official Newton's second law with this guy. Okay, but this F, remember, means net force. That's the most important thing about F equals ma in the data booklet. This is how it shows up in the data booklet, except without the vector bars, because that's the IB's deal. They want you to know what's a vector and what's not. Yeah, but when you see just F, it doesn't mean force. If you call the F in F equals ma force, you're not really doing, you're not really as detailed as you need to be. Okay, you need to know that F here is a net force. It's the sum of all of the forces acting on the object, at least, let's say, in the direction of the acceleration we are talking about. M is the mass of the object being accelerated. So if there's multiple like objects with multiple masses, you're talking about the M that's A-ing, yeah, where A is the acceleration of the object. This is the change in momentum of the object. Delta T, the time that it takes for the force to act. We sometimes call that duration. Okay, so the net force is a math thing. It's a sum of all the different forces acting on an object. It's not its own force. It's not like a physical force exactly. You wouldn't draw this on an FBD because the FBD just shows the actual forces. One object pushing on the object that we're drawing the FBD, we draw all of those. We don't draw the total as a separate thing. And if there's some kind of changing force situation, it's a little sticky to use this equation, but you can get away with it. The deal, though, if you do that, is you're going to get the average force. So we'll look at this a lot when we get to momentum and impulse and collisions. But if you use F equals ma and any kind of changing F is happening, the best you're going to get is an average force from this. But it's pretty useful sometimes if you need that. All right, so the deal with vector addition is we really can only work in one dimension at a time. There are some fun math tricks of how we can combine, but especially for now, we're just going to think horizontal or vertical. So we're going to use X for horizontal, Y for vertical. And here's really what you want to think about when you think of F equals ma. Again, it's a net force. So you're either going to focus on horizontal stuff and you're going to say, if I add up all of the horizontal forces side to side, that gives me, that's equal to the mass of the object times its acceleration side to side. And maybe, or sometimes you need both, which is fun. The net force vertically tells me about the acceleration vertically. Okay, in lots of areas in physics, this is kind of crazy, but the horizontal and vertical like motion are separate from each other. They really don't depend on each other. And so we can deal with one thing at a time. Okay, so you're either going to be setting up an X net force or setting up a Y net force. Sometimes you'll have to do both to solve the problem. But you never will add every single force together. Like you can't add vertical forces to horizontal forces, at least not just with regular addition. We will do that soon. Okay, and just remember when you're using ma, we're assuming m is constant. If m is changing, like you have a rocket ship or something, you need to use delta p over delta t, which we'll get to eventually. Okay, so let's look at some one-dimensional net force problems. Although it doesn't mean we'll only use one dimension, but it's only moving in one dimension. All right, so here we have a classic problem. Somebody pushing a box. All right, we're pushing a box to the right. 330 newtons is our applied force. We're given two different coefficients of friction because remember, there are two. Depending on the surfaces, the static one will be bigger. We're going to determine whether the crate will move, and if so, calculate the acceleration of the crate. All right, so a couple things going on. The first thing I want to do when I'm dealing with like, here's some forces stuff, find acceleration or something like that, is make an FBD. So here we have it started with a little crate. You can just draw a box or be as, detailed as you want in your crate sketch. Go nuts. But a box is perfectly great. And I want to draw all the forces acting on the object. So the one I'll always start with is gravity. There's a force due to gravity pulling straight down because the earth is that away and the weight of the box pulls down like that. And also I know if the box is on, the floor, there's also a normal force. I'm pretty sure in this case, those two forces are equal. We'll probably want to justify that because there's no rule that says they're always equal. In fact, I would say there's a rule that says they're not always equal. They're not. But it does happen a lot. Okay, but so I got a normal force. The ground is pushing up on the box to stop it from falling through. We said there's an applied force, so we'll draw it like this. I'm drawing it with the point of contact like on the left side of the box. So imagining somebody pushing it there to the right. That's the way to do it. And there's friction, which we're drawing along the ground. I drew these all roughly equal. I think we needed to do some math to figure out, whether the applied force is bigger than the friction force and so on. So you can kind of eyeball it. If we're being really, meticulous, we might even adjust later if we know that one is bigger than the other. But here we go. My 4 forces that are acting, that's the important part so that I can set up some math. Okay, so first, determine whether the crate will move. So they're asking me to do, some kind of math. Will it move? So I remember the rule for this. The rule for this is it has to do with static friction, because if I only push a little bit, static friction will resist me. But there's a maximum. There's a maximum static friction force. And I remember I can use the data booklet equation. So the data booklet equation is an inequality that the static force of friction is less than or equal to, but I'm going to do equal to because that'll give you the maximum. So the biggest static friction could be is the static coefficient of friction times the normal force. That's the size, the biggest size it can have, because it could be less than or equal to this. So I'm going to compare this to this. I'm pushing with 330 newtons. If this ends up being bigger than 330 newtons, that means it won't move. The static friction force could be even bigger, so we're not overcoming it. If that's less than 330, it is moving. So let's figure it out. So, okay, I'm always kind of checking along the way of what do I have, what do I need? This is what I'm trying to solve for, my unknown, if you will, FF's max, for right now at least. That's to help with this part of the problem. I know the coefficient of friction because it's just given, so I need the normal force. Well, how am I going to figure out the normal force? Well, the normal force is a vertical force. So we're going to have to make a separate vertical net force equation for this. All right, again, we can probably kind of see, because there's only 2 vertical forces, what's going to go on with the normal force, but let's spell it out to make sure. If I have a normal force in y, I need to do net force in y. Here's how we'll do this. I have to do net force equals ma to solve for like an individual force, like a normal force, which is a reactive force. Okay, so let's do this. The net force in y equals the mass of the object times its acceleration in y. When you do net force, what you do is you add up all of the vectors in that dimension. So I'm going to add up all the vectors in y. So I have 2 vertical forces. I have the normal force and I have the force due to gravity. And we're going to say up is positive and down is negative. All right. That's a convention. At least you can flip them if you really want, but that'll make life easy. All right. So now my net force is the normal force, which is positive, and then I subtract the force due to gravity because it's down, so it's negative, and that equals MAY. And let's do 2 steps at once here, because now I got to think about the object and anything I know about it. What's the vertical acceleration of the object? Well, even if it's moving with friction, it's not moving up and down. It's just moving side to side. And so since the velocity up and down is 0 and it's not changing, the acceleration in y is 0. Doesn't mean it's not accelerating, but it's not accelerating up and down. So this right side of the equation becomes 0. Okay, so this is how you always do it. Net force means go to your FBD and add/subtract all of the vectors in that dimension together, and then you set that equal to m times a. In this case, a is 0, so they equal 0, which is why, math-wise, you want to understand how this works, the normal force equals the force due to gravity here in this situation. Okay, but picture why if there's any other vertical force, or if you have some fun like vertical acceleration, those 2 things won't be equal. Okay, but here they are, so I know that equals m times g. So the normal force is going to be, well, let's just do that for now. All right, m times g, and we'll do it all at once. All right, so the normal force is m times g, so let's substitute that in to my equation, because what I'm trying to do, let's remind ourselves, I'm trying to find the maximum force of static friction just to see if it'll move. So I'm going to do the static friction force times mg, because we just found the normal force is mg big. Now we're good. I know m is 42 kilograms and g is in the front of my data booklet, so I'm just going to plug those in. Static coefficient of friction is 0.58. That was given. The mass of the object is 42 kilograms. I'm making sure I have the right units for everything. And then I got 9.8 meters per second squared. I know those are all base units, so I'm being a little sloppy, not writing my units out. But when you get used to things, you can do that sometimes. Make sure you put in base units. All right, so I'm going to multiply these all together. I go to my calculator, 0.58 times 42 times 9.8. And what do I get? I get 238 and change. I get like 238.7. That's 4 sig figs, more than enough newtons. So that's the maximum force of static friction. That's the biggest this can be. Well, I'm applying a force of 330 newtons, so I think no way it's not going to move because the applied force is greater than the static friction force. So the first answer would be yes. We can give some kind of justification like let's do it the other way. Let's say the applied force, Fa, is greater than F, the static max force of friction. So it'll move. That's a good enough justification. So it will definitely move. Okay, part 1 done. Haha, now part 2. If so, calculate the acceleration of the crate. Okay, let's do that. Now we know it's moving, so I know now that this is a dynamic friction. Okay, that's how it works. If it's not moving, it's static. If it's moving, then it's dynamic, and we're not going to use this 238 number at all. All right, that's not what's actually happening here. That's the biggest it could resist moving with, but since we got over it and it's moving, that's out. That's not happening. That was just our kind of check, our cutoff. So we need to deal with the fine acceleration now. Again, when you think F equals ma, you're thinking in y or in x. And the idea is going to be this thing is accelerating in x. It's accelerating side to side. So I'm going to use a net force in x equation to find the answer. So the sum of the forces side to side equals mass of the object times the side-to-side acceleration, which I know won't be 0 now because it's moving, and I expect one of these is going to be bigger than the other. Okay, net force in x, the left side of this equation means go to your FBD. This part means go to your FBD, take all of the x forces, which I have 2, right? I have a side-to-side force this way, the applied force, side-to-side force this way, the force of friction. We're going to call the applied force positive, friction negative, because we'll stick with our regular good old Cartesian, right is positive, left is negative thing. Flip them if you really want to be weird. Okay, but I'll do it like this. The applied force is positive, and then I'm going to really add a negative, so I'm going to subtract the force of friction. Now these are just, I'm not drawing the vector bar because now they're magnitudes. I put in the positive and negative signs, so I take the applied force, and I kind of add it to the size of the force of friction. I know that's going to be negative, so I'm doing it like this. Whereas here, this will still stay a vector because really I am getting this will tell me about the direction. If somehow, this wouldn't really make sense, but if somehow my force of friction were bigger than my applied force, my answer would be negative, which would mean a negative acceleration to the left. Well, it could be. It could already be moving. And that would mean it's like, slowing down or something if it's moving to the right and accelerating to the left. Anyway, let's go ahead and solve this now because I know the applied force. I can find the force of friction, which a similar equation, I just need to use this guy now because I know it's moving. Let's do a couple things at once. I always want to isolate my variable before I plug anything in. We're going to divide both sides by m. I'm going to do the applied force minus the friction force, and let's do 2 things at once here. I'm just going to do my data booklet formula for the friction force here. So applied force minus friction force over m is what I get for A. And I know the force of friction, because it's moving, is the coefficient of dynamic friction times the normal force. And there we go. Now I've solved it. Really, this is the solution. This is the important part. And using this like algebra part, you can really think through, what's going to happen. A bigger coefficient of friction would mean less acceleration, would mean because you have more friction. Apply a greater force, more acceleration. If the mass of the object is greater, you have less acceleration, all kinds of stuff like this. Okay, so this is the important solution. Now we should go through and plug in the numbers and see what number answer we get. So let's do it. The applied force is 330 newtons. My dynamic coefficient of friction, be careful, since it's moving, is 0.4. I'll multiply that by the normal force, which we found over here, which was m times g. So 42 times 9.8. Divide that all by the mass of the object, 42 kilograms. I think we're good to go. Okay, and calculator, I will do this all at once on my calculator. So like, parentheses 330 minus parentheses again, just to be safe, 0.4 times 42 times 9.8 and parentheses slash 42. That should get you there. Should get you to 3.937, something like that. And so now to finish it off, sig figs. So all of my values have, 2 sig figs. So we're going to put our answer to 2 sig figs. So the acceleration of the object is 3.9 meters per second squared. And it is a vector, so I should really say to the right. There we go. All right, so fun. There's F equals ma with some vertical stuff and horizontal stuff together. That's pretty common because friction and the normal force are perpendicular, so a lot of times you got to use both. Okay, let's do one other kind of solvey one. Okay, so a helpful problem for everyday life. You find yourself walking by a vat of maple syrup and you drop a marble into it and it sinks down to the bottom. Okay, so I'm given some values here and oops, I didn't put this in here, but I will put it in there. What we need is the density of maple syrup, which Google told me is, where did it go? 1370. All right, so I'm also going to need this. The density of maple syrup, fun fact is 1370 kilograms per cubic meter. Okay. Spoiler that we're going to need that. Okay, but I'm given viscosity, the mass of the marble, the diameter of the marble. So determine the terminal velocity of the marble as it falls through the syrup. Whoa. All right, so terminal velocity. I want to remember what that means. And that's what happens when something is falling at a constant speed. That's the key thing. We looked at this a little bit with like motion graphs and dealing with something that's just falling through the air at terminal speed. It's even a little more fun in a liquid like this. Okay, so I know it's falling at a constant speed, so how is that happening? Well, let's draw an FBD and think about it. Okay, there's my marble in my vat of maple syrup, and the reason it's like falling is because gravity's pulling it down, yeah? So the force due to gravity, I'm definitely going to draw. Okay, why does it fall at terminal speed? Because if that was all that was happening, it would definitely accelerate, right? The only way you go at a constant speed is if your acceleration, and we'll probably say vertical acceleration here because we know we're falling up and down, is 0. That's really the key for terminal velocity. So the acceleration is 0. And if I think net force equals ma, my net force must also be 0. So I have some upward force or forces that are going to essentially balance gravity is what it's going to work out to be. So I'm thinking about the physical situation of what's going on and what other forces would act. Well, it's in syrup. So there's a couple. First, there's one that we talked about, a buoyancy force, because it's like in a liquid and it's displaced some liquid. So there will be an upward floaty force on it. And there will also be a drag force. There's 2 vertical forces because it's in a situation where both of those will happen. It's submerged in a liquid, so there's a buoyancy force, and it's moving through a liquid, so there's a viscous drag force. So both of those are upwards. Okay. So that's like the concept of how I set up this FBD. And now, this one might look a little crazy, but it's probably a little more straightforward than the last one, really. Because all I need to do now is do F equals ma on my FBD, which means the sum of all the forces either up or down. Well, I definitely want to, there's no forces left or right, so I want to deal with up and down rather than side to side. So we'll do the sum of the vertical forces equals mass times vertical acceleration. I know this part's going to be 0, which is going to help me solve. What are my forces? Well, I got 3 of them. I got 2 upward forces and 1 downward force. I'm going to stick with up as positive, down as negative. So I got to do the net force in y. I look at my FBD. I have 1, 2, 3 y forces. I add 3 terms. So I have the drag force, which is positive. I have the buoyancy force, which is positive. And I have the force due to gravity, which is negative. And that equals m times ay. I know ay equals 0 because of this. Its terminal velocity, constant speed is going to fall with. So that all equals 0. Okay, in other words, again, because no acceleration, the downward forces equal all of the upward forces together. So we can do this, drag force. Yeah, let's do this first, because I don't necessarily know that we want to solve for that. We'll do that step, but let's plug in the formulas that we have for these. Okay, so the drag force, I go to my trusty data booklet, I can find the drag force with Stokes' law, which is 6 times pi times viscosity, this crazy eta thing, times r, the radius of the sphere, times v, the speed that it falls at. Ooh, useful. Okay, there's drag force. Now let's do the next one. The buoyant force is equal to, again, data booklet tells me density of the fluid times volume of the fluid times g. I do need to know what all these mean. I gotta know that's like density of the fluid, and that's the volume of the displaced fluid, and that's like the radius of the sphere, you know? So I know the context of all those. Minus mg for force due to gravity equals 0. Okay. Why am I doing that? Because what I'm trying to find is terminal velocity, and I'm thinking the speed that the marble is falling at is this terminal velocity. So I'm solving for this v. I think I know most everything else. Let's see. I know the radius, so I know the diameter, so I can get the radius of the marble pretty easy. The density of maple syrup, I just Googled, and there it is. I'm pretty sure I can figure out the volume of maple syrup that gets displaced. It's going to be equal to the volume of the marble. I'm going to do like some fun volume of a sphere stuff. G is a constant, and I'm given the mass. So we're good to go, really. Now it's just a math problem. We're going to solve for V. That's it. All right, so let's do it. Let's solve for V. I am going to get these terms over to this side. So I'll do a couple math steps at once. I'm going to subtract rho Vg and add mg. So I got 6 pi times viscosity times r times v equals, I'm going to do this way because I don't want to start with a negative, Vg, right? So I added mg, I subtracted rho Vg. And let's be good physics students and do all of our algebra at first. So we want to divide both sides by everything but the v. So I want to divide by 6 pi eta r. All fun. All right, so the terminal speed of this thing is mg minus rho vg over 6 pi eta r. Oh boy, fun. Okay, but that's it. Do be careful too. I'm being a little sloppy. This is very fun because notice we got two V's. I got a capital V for the volume of liquid. I got a lowercase v for the velocity, or I guess really we should say speed of the marble. And that's the one I'm solving for. So that's like big V, that's little v. All right. Now, though, we can really start plugging stuff in. The only thing we're really going to need is like volume of the sphere and deal with the radius thing. Okay. And units. So I am going to put, we should probably put units here to make sure we're being okay. All right. 2.3 grams is the mass, but I want that in kilograms. So I'm going to call that 0.0023 kilograms. And then I multiply by 9.8 meters per second squared. And I subtract the density of maple syrup, 1370 kilograms per cubic meter, times the volume of liquid that's displaced, which is going to be the volume of a sphere. So I'm kind of out of space, so let's do that over here. I want to find V, the volume of liquid. I'm going to use the volume of a sphere formula, 4/3 pi r cubed in the front of your data booklet if you need it. So I'm going to do 4/3 times pi. All right, radius. I'm given the diameter of 13 millimeters. My radius will be half that, so 6.5 millimeters. And I do want it in base units, yeah? So here's how I'm going to do all my prefix stuff. The front of the data booklet tells me milli means times 10 to the minus 3. That's what millimeters means. Times 10 to the minus 3 meters. This is probably an easy enough one to convert with some 0.00065, whatever. But I really want to, what I really want to do is use this because it's just going to make my life easy with all different conversions. Okay, so that's millimeters. I cube the R to get my volume here. And I'm going to go ahead and plug those in. So let's see. All right. In my calculator, I'm going to do 4 over 3 times pi symbol times 6.5 big E minus 3 cubed. And I do believe I get 1.15 times 10 to the minus 6. It's 150, so I'm pretty comfortable writing that like that. And that is cubic meters. Okay, there's the volume. All that to plug that number in down here. 1.15 times 10 to the minus 6 for volume times 9.8. And that's meters cubed, and that's meters per second squared. And then I'm going to divide all of that, oh boy, by 6 pi eta r. Again, r is going to be, oh, let's just put those numbers in here. I have all the other numbers. R is just going to be half of the diameter. And make sure I put it in meters. Okay. This guy's in base units. Pascal seconds is what we said the units for viscosity are. And Pascal is like a Newton per square meter, so we're good. And then I'm going to multiply by the radius of the thing, which again is 6.5 times 10 to the minus 3. Because it's 6.5 millimeters. Okay. Now, you know, fun math, fun calculator math. Yeah, let's plug it in. We're going to do 0.0023 times 9.8. Take what I get there and subtract 1370 times 1.15 times 10 to the minus 6 times 9.8. And take all that and divide by 6 pi over times 0.15 times 6.5 times 10 to the minus 3. For sure in a calculator, make sure if you're doing this that like if you get an answer and then you do divide by, put parentheses. Because if you say, you know, whatever to whatever, and you tell your calculator, whatever, divide by 6 times pi times 0.15, so on. Your calculator is going to follow order of operations. It's going to do this division, and then it's going to multiply by this. You don't want that. You want it to divide by all of this plus that, so put parentheses. All right, anyway, crunch some numbers, and I'm pretty sure you should get an answer of, where did it go? I lost it. 0.386. That sounds right, because this equals the speed. 0.386. We got 2 sig things and all our things, so we can round that to 0.39 meters per second. Okay. So the end becomes lots of, you know, algebra and math and plugging in numbers, but the concept right here, that the force of gravity is equal to the combination of the drag and the buoyancy force, and I got formulas for all of them. That's really all we're doing. Yeah. And because V, speed, is in the drag equation, I can solve for it because I know if it's falling at a constant speed, these forces are balanced. Okay, fun one with lots of forces. Let's do one more quick one for you to try. This is a real paper 1 question, like a multiple choice IB test question. So think about this. An object of mass 8 kilograms is falling vertically through the air. The drag force on the object is 60 newtons. What's the best estimate of the acceleration of the object? Right? So go ahead, give this a shot, pause, and see what you come up with. Okay, there's a trick here. The trick answer is C. C is super wrong. C is if you think F equals MA just means F equals MA. You're like, oh, F equals MA. I got an F, I got an M. So all I would do is F over M, right? So I would do 60 over 8, right? And get 7.5. No way, super wrong, terrible. F equals MA doesn't mean F equals MA. It means net force equals MA. So what do I need? I need an FBD. So here's my object. My object is falling. So it's moving like this way. I'll draw this off to the side maybe. So I have a couple forces happening. There's a drag force, which is going to be opposite V. There's like an upwards force as this thing falls, 60 newtons. But why is it falling at all? Well, it's falling because, as always, there's a gravitational force pulling down on it. And how big is the force due to gravity? Well, it's mg big. The mass is 8. For like a multiple choice question like this, you would typically just use 10 for g because we're estimating. So that's about 80. 8 times 10. So I have 80 down and 60 up, which means my net force is 20. Right? Down. I do 60 plus negative 80, something like that. So I get negative 20. The net force is 20. Now I can find acceleration by dividing that by the mass of the object, and I'm going to get, 2.5 meters per second squared. So I'm going to get B. Okay, moral of the story, F equals ma. The F doesn't just mean force. It is very important that that means net force, the sum of all other forces. So you need an FBD to draw, to solve, and have a happy, happy physics life. All right, so there's a bunch of math and equations and examples for you as we start getting into forces and FBDs in a fun way. So go digest that, practice a little bit, and have fun.